Hello everyone, welcome back. In the previous example, we explained how we use the information regarding to the Miller indices in order to find the planes and then the rest of the information. Now we solved 3.666, which we had the crystal structure. Then based on the crystal structure, we found out the planes and the rest of the requirement. Now we can solve another type of XRD analysis when we don't know the crystal structure. So we're going to find the crystal structure. Now if you don't know the crystal structure, you will not know the pattern of the Miller square summation of the Miller indices. You don't know that. So if you don't know the pattern, you will not be able to find the plane. Now, in order to find the crystal structure, the only thing that is related to the crystal structure is the sum of the square Miller indices. Now we know that if you have simple cubic, just do somewhere here, we know that if it's simple cubic, if it is BCC, if it is FCC, we know the arrangement. I mean, this is going to give us, which we call them the H square plus K square plus L square. Let's do this manner. We know that this is going to be 1, 2, except 7. We don't have 7 inside here, so that's going to go in this manner, but 7 is not included. 7 is not included. We said for this, going to go 2, 4, 2, 4, 6. And so on. For FCC, we said it's 3, 4, 8, 11. Then it's going to repeat itself in the manner. Will be 12. Is it? Will be 16. Then will be 19. And then we'll go further. We have them. We'll write them when we need them. So first, after 19 will be 20, then will be 24 and 27 and so on. Now we know those patterns. Those are the patterns that will help us to find the crystal structure. Those are the patterns that will help us to find the crystal structure. So if I get these patterns, I know which crystal structure I have. But how can I get this pattern? How can I find H squared plus K squared plus L squared? Now recalling the equation that we have it. We're going to say that, now remember in the previous example we solved a case that we had this one, 3.66, we had a crystal structure, we found some information. Now the only way that we can find H squared plus K squared plus L squared is from the equation of DHKL. DHKL is equal to A over H square plus K square plus L square. Now I'm looking to find this one, this value, H square plus K square plus L square. The problem is that we don't have DHKL, we don't have A. Now we have another equation which we know that n lambda is equal to 2 DHKL over sine theta. Now from the pattern, what we will get theta. We have from the pattern, from the XRD analysis, we have theta, we have lambda, we have n. Again, DHKL is not unknown. So if we bring, instead of this DHKL, we'll put this equation we still have some unknowns, but we can rearrange it. So I'm going to bring this into this equation and just rearrange it in this manner. So the root h squared will be in one side, plus k squared plus l squared, the sum of the square of Miller indices from one side will be equal to n it will be 2a sine theta over n lambda. Now if you square to get rid of this root here, on this side will remain h squared plus k squared plus l squared. On the other hand, we will have 4a squared over n squared lambda squared, it's going to be lambda squared, and that's going to be sine square theta. Now some information here required. Again, we cannot find it. Why? Because we don't have a. A is the problem. We don't have a, so we have theta, we have lambda, we have n, but we don't have a, so we cannot find the h squared, k squared plus l squared values. What will we do? Now this value here, 4a squared over n squared lambda squared, they are constant for the XRD pattern. Why? Because we said that we have one element, and the elements that we have it has one crystal structure. I mean, the pattern that we have it here, that we are studying here, is for an element, for a metal. Remember, chapter 3 mainly was focusing with metal. So we have only one crystal structure. So if it's one crystal structure, it means that every single peak, they have the same crystal structure. If they have the same crystal structure, the same metal, so A here is equal to A here, equal to A here, equal to A here, which, if you remember, we did it in the example 3.66. We found all the A's were similar, and we said that they had to come close to each other because A is constant. Now n, order of reflection, is constant, wavelength is constant for all the values, all the peaks. Now, in order to find this h squared, k squared plus l squared, what will we do? Now, we have this pattern. Now, we will divide the second peak, I mean all the peaks, h squared plus k squared plus l squared by the first one. So what do I mean by that? I know that this is the equation of h squared plus k squared plus l squared equal to 4a squared n squared lambda squared sine squared theta. So if I divide two h squares over each other, what will happen? So if I divide this one, let me see if I can. Now, if I divide this by exactly similar, let's just divide it here. If I divide this one by another h squared n square wavelength square sine square theta. Now, if this is for the first peak, and let's say this is for the second peak, this is for the first peak. What will happen if you divide, if you check here, if you divide the second peak, h squared plus k squared, you're dividing it by the first h squared plus k squared plus l squared, what will happen? Those two, they are constant then they're gonna cancel out each other. The remaining, which we call it, will be like this: sine square of the second theta over the sine square of the first theta. Sine square of the first theta. So if I divide everything by the first theta, by the first one, we'll get sine square, for example, third theta over the first theta, and so on. So we're gonna find this term. We're gonna use this term to find what? To find this pattern. Now let's divide them. Let's say if I divide those values, for example, if I divide everything by the first one, I mean even this one, see this one also divided by itself. Now if I divide everything by the first one, for simple cubic they will be the same. Yes, they will be the same. For BCC, what will happen if I divide everything by the first one, this divided by itself, and everyone will be divided by the first one, you will have a pattern like this. Now you're gonna see what's the difference between them. And for BCC, if we divide everything by the first one, you'll get another pattern. So we'll look for this pattern. We will look this for pattern. Those patterns are the one that we can find them, and we find those, we know which crystal structure we have them. Those are the pattern that we will get them. I mean, if I divide sine square theta by the first one, we'll get those numbers. Those numbers we'll get them from where? Those numbers we will get them if we divide all the sine square theta by the first sine square theta. I mean, even itself, the first one by divide the first one will be 1, and then the second one by the first one, third one by the first one, and so on. We will find a pattern, and from those patterns we'll be able to know which crystal structure we have it. Now we're gonna solve 2 questions to see how we're gonna realize which crystal structure we have it. Now those blue one will be our aim. We're gonna see them. Now I'm gonna explain a question which was a midterm. No, it was for spring semester last year. It was a long duration I gave it to them, so the question was longer than longer than what was here. Now let's see what's given and what's required. Table below represent the results of an XRD diffraction experiment in the form of the diffracted peak versus the diffraction angle. So we have peaks, we have 8 peaks, and diffraction angle. Diffraction angle will be 2 theta. Remember, that's 2 theta we have it there. Then if X-ray with a wavelength of 0.15454 nanometer, so I gave it in a long. Why? Because I wanted the numbers come out exactly similar. We'll see it in this example. So this is the wavelength lambda, and then determine the crystal structure of the metal. We need to find the crystal structure of the metal. We need to find the indices of the plane that produces each of the peaks. So we need to find the planes, and then the lattice parameter, which is A, and the element that the XRD represent. I mean, which element is this? It's belong to which element? Remember, we only gave you a pattern for one element. For the actual life, it's much more complicated than the one that I'm explaining it here. It's a simple XRD analysis we're doing it. So we only have the peak numbers and the diffraction angle, 2 theta. We have to find all of the other information that we have it. Now we're going to use what? We're going to use this technique. We're going to use the sine square in order to know the crystal structure, to see how does it work. So let's say the angle we have we're going to create a table like this. Now in order to find what we're looking for, because if we want to find dividing every sine square by the first sine square, this minimum, we're going to explain this, it's the first one. This minimum is going to be for the first one. You can write it sometimes first. I'm writing it first. I mean a sine square of the first peak. Now, In order to do this one, this is 2 theta, remember, this is 2 theta. We'll find theta. Theta will be what? Will be those divided by 2. So if you divide them by 2, you'll get the answers. 31 divided by 2, you will have it here. You'll have it here. Now, we're going to find, we'll take the sine. You can directly go for sine square. I mean, instead of doing it one by one, you can directly do the sine square here. You directly do the sine square, you will get them. Or you can calculate sine and then square it. Be careful, please, do not square the angle. Do not square the angle. You have to take, so the square is for the sine, not for the angle. So if you don't know how to square a sine on your calculator, I recommend you do the sine, find the sine, then square those values. Square those values, so you'll not have any problem. Then, we're going to divide everything. For example, those are the sine, the square we have them, yes, the sine square. So we're dividing this one. This is the minimum, yes, this is, we call it the minimum one. This is the minimum, or the first one. We will divide everything we have it by the first one. So if I decide, for example, divide the first one by itself, it's going to be 1. It's going to be 1. If I divide everything, this one by itself will be 1. If I divide the second one by this, you will try it, it will be 1, 3, 3, 3, something like this. Divide the third one by the first one. Remember, you divide everything by the first one. So you'll divide this like this. You divide everything by the first one, and you will get the pattern. Why? Because we say sine theta squared over the sine theta squared of the first one, of the first peak. Now, if you do all of them, you're going to have this pattern, something like this. 1, 1.333, 2.666, something like this. Now, in order to know which one is it, basically the fraction will happen in which one? Fraction happen in FCC. But in order to be sure that you will get those values, multiplied by 3, because this is the first number that, in order to get this peak, in order to get these numbers, we divide everything by 3, yes? To get all of these numbers, we divide it by 2. Divide by 2. In order to get all of these numbers, we divide it by number 1. So in order to get back those numbers, multiplied by 3, to see whether we're actually getting back to see. So I'm going to say that this will be equal to this one times 3. Times 3. I'm getting 3 here. If I do this one for the rest of them, you will see that I got 4, 8, 11, 12, 16, 19, 20, which I know this is representing what? Representing an FCC crystal structure for me. So what we did, we found the sine square theta for all the peaks, then we divide each peak's sine square theta by the first one. It's going to give us some numbers in order to be sure that which number they are. So some people, they explain in this manner. Some they explain in this manner. Some they explain this manner. They say that multiplied by multiplied by 2. Multiplied by 2, you don't get something. Multiplied by 3, you will get those numbers. Look, you will get it like this. 3.9999 is almost 4. Or 18.999 is 19, or something will be. Why? Because those coming from where? From the digits that we have them in the calculation. So they will come, because you have to take full digits here. I mean 5th digit or 6th digits of the angles, then those will come exactly for. But it is okay. Like if you see like this, 3, 4, 8, 11, 12, 16, 19, 20. This is, we call it FCC crystal structure. So you can directly multiply it by 3. Multiply it by 3. Why? Because fraction happens where? Happens in the FCC. It's not going to happen in BCC, and it's not going to happen in simple cubic. You're only responsible for 3 crystal structure here. Now, I need you to multiply it by 3 in order to see. Why? Because I've seen it. Some students, they found fraction. They found this one to be 1 point, for example, 2. Define 1.2. It's okay. It is gonna be. It is going to be crystal. What do you call this? It's going to be an FCC. Why? Because it shows a fraction. No, it does not mean that if you have a fraction, it will be FCC. You have to make sure that multiplied by 3 to see whether you're getting it or not. So this is indeed is what is this one multiplied by 3. We multiply this by 3 in order to be sure that we're multiplying by 3 in order to see that whether we're getting this number. So not all the fraction will be. Why? Because if you made a mistake here, you will see it from here. Maybe you have this one 3.3, so it's not going to give you 11. Yes, you know that you made a mistake somewhere here. You have to fix those problems. So do not just, okay, you saw fraction, say this is an FCC crystal structure. By the way, if you only do this, will be enough. If you, for example, found 2.666 multiplied by 3, you found this is going to be, let's bring it back. Yes. So you don't need to finish all of them here. I mean, if you can guess the pattern, which one is it, that's enough. I mean, if in order to know exactly, make sure you find them. If you want to see that if you haven't done any mistake here, find all of them. This is check for yourself. Find all of them to make sure that you haven't done any mistake here. Then you can continue with the rest of the other things. So, if you find them correctly, you will get the pattern, and this pattern we call it FCC. Now, if it's FCC, the rest will be easy, yes? Why? Because the question says that find the crystal structure, which was the hardest thing, and then the indices, we showed you how do you find the planes, and then the lattice parameter, and the rest of the things that we have. In order to find the planes, what do we say? We said that we're going to find 3 numbers, again using FCC crystal structures rule, that we said that the rule says, and for FCC crystal structure, diffraction will occur when HKL and HKL, they are either odd, all, even, or all odd. This is the case that will happen in FCC crystal structure. So all even or all odd for the plane Miller indices. So we know that this is going to be 111, 200, 220, and then 311, and then 222, 400, 331, and 420. Those are, we know them directly, so we're going to just write them down the way it is: 111, 200, 220. You do the summation, their square will be those number, and they look at them, they are all even or all odd. This is the HKL. Then you want to find in order to find the what's required there, require the lattice parameter, which is A. You can directly find A, or in order to find A, you will find D, then you will find A. That's possible. I mean, it's up to you. So in order to find, you can directly find A. Why? Because 2 equations we have it in order to find A, and we know the equations that we have it. A will be found from this equation, but it needs DHKL. So you first have to find DHKL, then find A. Or bring this one inside here, rearrange it for A, create an equation for yourself, and then find A. But remember, I need for one peak the calculation for those things. For DA, I need and this showed to me in one. For example, you found sine squared, those things. I mean, for one of them you can show it to me. For one peak, I need with the equations, and the rest of them you can fill the table easily. Now, finding D, if I'm finding DHKL, if I want to find DHKL, I can use this equation here. Why? Because I have n lambda, I have sine theta, so I can find DHKL, then I can find A. I prefer in this manner. In order to find DHKL, we'll say n lambda divided 2 sine theta. I have the theta, so I can calculate them. Then those will be D. Those will be the value of D. So I need you to at this right for me 4 digits required. Then if you find A, you will see all the A's will come close to each other. So at least 4 digits of them that are equal. The 5th digit may be different. I mean, the 5th one, it's okay to be different. Here, even some of them, the 6th one different. 6th one different. Why? Because we took the angles in 4 digits, so the precisions are good here, and all the A's will come close. And it has to be. Why? Because we said it's one crystal structure. A will be the same. A will be the same. Now the last thing, if you want to find element here, because the question is, the thing says that find the element of the XRD. So how do we find elements here? How do you find elements? In order to find element, we're going to use the table. We're going to use the table that we have it, table of material properties. We will use the crystal structure and the atomic radius to find the element that we have it. So in order to find the element, we need the crystal structure. We already have the crystal structure, is FCC, we found it. We need R, which is the atomic radius. We found this one. Let's find R, and then we're going to go to the table and find the element for this pattern. Well, in FCC we know that A is equal to what? 2 root 2R. Then we have A, we can find R, which simply will be A divided by 2 root 2R. Sorry, 2 root 2. Will be A divided by 2 root 2. And we have all the A's, we found them. By the way, you don't need to find all the A's here. Pay attention here. Find 2 just for checking. So I'm going to give the student, find for example A for the first peak and for example 7th peak. If you got similar answer, that's it. And for R is the same way. For R is the same way. I don't want you to find all of the R's. No need to find all of the R's. No need to find all of the R's. Again, because if A's are equal, A also will be equal. And look at them, 175, 175, 17499 will be 175, 175. The R come exactly all 175 here. So if you just find 2, will be enough. I need you to find 2 for checking. So in order to know whether you did correct or not, you need to randomly choose, or I will ask you to find from 2 of the peaks, find A and R. So look at them. If those 2 chosen, we know that they are correct. They are come out exactly similar. Now the atomic radius is 0.17775 and the crystal structure is FCC. So if you're going to find the element, we're going to use the table that we have. There's a table which is in the 2nd page of the textbook that we can ask you to find. You know where is it? This is in the 2nd page of the textbook. Now I'm looking for what? Looking for 2 things, an FCC crystal structure and atomic radius. So there is atomic radius. We're looking for 175. We're gonna come down. We have 175 here. Let's see if you have another F175. We don't have any other 175. If you check, it says FCC crystal structure. If it's the one that we have, yes, we have an FCC crystal structure with atomic radius 0.175. So the element that we have it is lead. This is how we analyzing XRD pattern, but this is for one element. That's why it's easy. In reality, we have a compounds, a lot of combinations, so you have to use a computer-based program in order to analyze the crystal structure, the elements, the compounds, which by hand will be, we cannot do it. Why? Because we have 7 crystal structures with a 7 crystal systems. With the crystal structures, they will tell us that 14 Bravais lattices. There's 14 different cases. We only did for what? For 3 cases. Those are easy because they're cubic. The rest of them are not cubic, so you will struggle. You will struggle with if you do it by hand. That's why we're using software base to do it. Thanks for watching.